Okay, thank you everyone. Okay, thank you everyone for attending today's past seminar. It's our honor and pleasure to have our speaker, Professor Songjin Choi, who is an assistant professor in the Department of CEE in the University of Minnesota. Professor Choi graduated from Korea Advanced Institute of Science and Technology with PhD degree in CEE. And after that, he has had the experience of being a postdoctoral researcher in both the Korea Advanced Institute of Science and Technology as well as in McGill University. And his research is quite interesting. He works at the intersection of multiple areas that includes urban mobility data analytics, data modeling, deep learning, artificial intelligence, and connected and automated vehicles. And he also works on optimization methods that contributes to the development of sustainable and efficient urban transportation systems. So I think today we have a very exciting topic of the talk related to generative AI models, and the floor is yours.
All right, thank you for inviting me, and thank you so much for the introduction. My name is Songjin Choi. I'm an assistant professor at the University of Minnesota. It is my great pleasure to present my research that I did from my PhD through my postdoc and what I'm currently working on. I just want to say this. So I graduated from KAIST, Korea Advanced Institute of Science and Technology. And I'm pretty sure around the world there are many institutions like this, but unique thing about KAIST transportation program is that at least when I was there, all faculties were from UC Berkeley. So my supervisor, Professor Hwasu Yeo, did his PhD with Alex Garbadonis, and there was Yoonjin Yoon who did, I think, Mark Hansen, and Professor Ki Tae-jung who did with Professor Michael Cassidy. And the next one they hired was also from UC Berkeley, who is Professor Jinwoo Lee, who did PhD with Samuel Madanat. So it's like, so Berkeley has been like a dream place for me while I was kind of building up my career as a researcher, because I heard a lot of good things about Berkeley and was amazed by all the research that you do there. So it's my great pleasure. So I work on the intersection of AI and transportation, and especially nowadays, I'm working mostly on generative AI side and how to apply generative AI to do or to model transportation data. So let me kind of start with this let me start with my presentation with this description. So when we think about data, data comes from real world. And as a researcher or as a modeler, we are trying to build some kind of model that represent the real world from data, right? But then what do we do with this model? So let me take this example of traffic flow theory and traffic simulation. So we have traffic, highway network, and highway traffic, and then we collect data, NGSIM or detector data like Caltrans PAMS, and then we develop traffic flow theory. So this is from my supervisor's work, what he did for his PhD of like asymmetric traffic flow theory. So they developed this kind of theory around the phenomenon that comes that they can identify in the data. And then what they do is they develop some kind of traffic simulation. So essentially, based on the knowledge that we build up from this kind of data, we are kind of trying to generate new type of data so that we can kind of use our knowledge around the data that we observe. So essentially, we are generating synthetic data to represent the real world and to understand the real world. So this really kind of summarizes all my research. So if we think about real world and data, we can think of real world as distribution and data as sample of distribution. And all the efforts that we do as a modeler or researcher is to understand this distribution of the real world from limited samples or sample, which is the data. So then we have to kind of think about how we can learn this kind of data so how we can learn the distribution from data. So most straightforward way is to assume some kind of probabilistic distribution and or estimate the distribution parameters. So for example, on the left here, we have Gaussian distribution. And if we have some kind of data, we can fit the variance and the mean, and then we can represent the data using Gaussian distribution. Or this is my work of predicting traffic flow or traffic speed and traffic flow. We can also use more complicated parametric distributions to represent the distribution of the data. But then what's more interesting nowadays is that we can actually learn this kind of distribution by training a neural network that can produce similar properties to the given data. And this is known as sometimes deep generative model or sometimes generative AI. So this is a famous quote from Richard Feynman. I think it was left on his chalkboard when he died or something. So it says, "What I cannot create, I do not understand." So because we know if this statement is true, the contrapositive should be true, meaning that what I don't understand, I can create. So if you are building AI model, or if you are building a model that represent the distribution of the data that we are collecting, and if the AI understands what the data is, what the distribution is, it should be able to create and generate new type of data. So that's the core idea around this deep generative model, where the goal is given some training data drawn from some distribution, we are trying to train a model that either estimate the distribution parameter or distribution directly, or I can also say that it's estimating the likelihood of the data samples, or we can train a model that can generate new sample from the same distribution. So if we have a training data here, the goal of deep generative models are training this P model X, and then we use P model X to sample new data, which has the same distribution, similar distributional properties to the original data that we observed from the real world. And around like 10, 15 years, from like 10 to 15 years ago, people have developed lots of different type of generative models, and usually they can first divide it into two things. One is explicit density model, and the second branch is implicit density model. So the explicit density model tries to use the likelihood function during training, while the implicit density model doesn't use likelihood function and just maximize employ some kind of alternative method to theoretically achieve the goal of maximizing the data likelihood. And if we further kind of break this down, we have tractable explicit density model and approximate density model. And where we perform exact and direct likelihood computation, and the approximate density model we use some kind of approximation method due to infeasibility of exact likelihood computation. So there are some examples like normalizing flows in tractable density model, diffusion model, which is one of the state-of-the-art model nowadays in image generation, which falls under approximate explicit density model, and generative adversarial network, which falls under implicit density model. And there are some properties that we expect from this kind of deep generative model. One is high quality sample, and the other is fast sampling, and the next one is mode coverage. So high quality sample means that if we generate some kind of data, we want that the generated sample to be in high quality. And we want to generate those samples fast enough so that we can do some kind of real-time decision-making or real-time inference. But still, we also want the model to cover all the modes. If the data distribution is multimodal, we want the model to cover all the modes in the distribution. And even though there are many different types of generative model, they don't usually satisfy all of these criteria. So, for example, GAN usually produce high quality samples and can do fast sampling, but it has some problem with mode coverage. Diffusion model, on the other hand, they produce high quality sample and has some theoretical guarantee of mode coverage, but then it has slower sampling speed. While normalizing flows, they do fast sampling and a good mode coverage, but then they sometimes get attacked by the quality of their sample. And when we are trying to apply this kind of deep generative models in transportation research. In this paper that we published this year, we identified 3 different applications that we can use deep generative models in transportation research. So the first part is, as the name suggests, we can use deep generative model to generate data. The second part is, because the deep generative models learn the distribution of the data, we can use it for some probabilistic inference. And the third pillar is, as a byproduct of this learning process, usually the models have some kind of latent vector or latent representation of the data. So we can use that latent vector to represent the data, meaning that we can do unsupervised representation learning. So today's talk focuses on first two pillars of the applications of DGM, one focusing on data generation and one focusing on probabilistic inference. So the first study is one of the chapters that I had in my PhD thesis. The second study uses another model called normalizing flows to do probabilistic inference of microscopic trajectories. And I'm going to talk more about the rationale of the third part, but essentially we are using diffusion model for traffic state estimation. So when I was doing my PhD, actually my whole PhD was not about generative model. It was more about how to use trajectories and how to use trajectories more wisely so that we can understand traffic phenomena. So I defined this urban trajectory. So it's a trajectory that represents the mobility behavior of a user. So if you look at this individual trajectory, already we can get pretty large amount of information, such as origin and destination of this person, maybe travel time, and maybe depending on the data set, it might have some kind of speed profile. We also understand the routing patterns, things like that. But what's more interesting is when we combine a massive amount of trajectory data and then form this group of trajectories, then this group of trajectories kind of represent the overall urban mobility pattern, so that we can extract some things like travel time distribution, regional traffic volume, traffic flow, OD distribution, dynamic OD distribution across different time of day, and different routing patterns that occur in the urban system. So one of the topic that I worked with trajectory data is to generate trajectories of these individual agents by using this trajectory data. But then if we think about this ability to generate trajectories of individual agents, it's not a completely new topic to transportation researchers, because in the past, we couldn't really observe this true trajectory. So we relied on some theoretical models, especially network traffic models, including trip generation model that generate the origin and destination, and route trace models, and some traffic flow theory or microscopic driving behavior model to simulate the vehicles. And by kind of combining these components, we can simulate the data or simulate the traffic, and then we get the simulated trajectories. And we hope that the simulated trajectories can match this unobserved true trajectory. But this method, even though it has been very successful, it has several limitations. First of all, there's this complex model building process, and also it requires a lot of effort to find the right model parameters associated with each model component. And then sometimes they rely on strong behavioral assumptions, such as people always find or people always prefer like shortest travel time. And also sometimes they rely on simplified physical process models, such as approximating the dynamics into first order equation, things like that, which limits the performance when it comes to actually trying to simulate the traffic network. So what if we have like an infinite transportation and mobility data and infinite computing resources to run this kind of or train this kind of AI model? Can we do better than what we have done so far? So, and actually, we are getting into the era where we get this massive amount of trajectory data and all sorts of transportation and mobility data from connected and automated vehicles and Internet of Things. And we have great computational resources using fast parallelization of GPUs and everything. So actually, the idea is to directly use this observed trajectory data to learn a model that can generate this trajectory data without relying on some behavioral assumption, and to understand more complex nonlinear spatial temporal features in trajectory data. Actually, there has been other studies that also use data-driven method to predict or to generate this kind of trajectory data. Usually what they did was they have a sequence of previously visited location. So they kind of formalize the problem into next location problem. And then sometimes use recurrent neural networks. Nowadays they use transformers to predict next location of agent, so that when they have a full trajectory, they can call it a full trajectory of an agent. But quickly, if you can kind of imagine, it has a critical limitation that the error gets accumulated as you go through trajectory prediction. And even though you have a small error at first few steps, this small error kind of deviates a lot, and then finally, when you compare the actual full trajectory with real trajectory, then it'll not be realistic. So the idea of the study was to consider the distribution of expected future trajectories. So meaning that we want to kind of embed the multimodality in the trajectory data in this generation process. So the model I developed kind of combines the idea of from previous study of encoding information from previously visited locations by using recurrent neural networks. And we use generative adversarial imitation learning, which is similar to GAN, the generative adversarial network, to embed the distribution of expected future trajectories into generation process of this kind of trajectory. So GALE, generative adversarial imitation learning, is a combination of generative adversarial network with inverse reinforcement learning. I'm not going to go through the details of what the model is, but the idea is that we have two neural networks. One is called generator, and the other one is called discriminator. So generator tries to generate realistic data as much as possible. And then discriminator tries to distinguish the generated samples from real samples. So they have opposing objective. And by doing this kind of competition between generator and the discriminator, finally, when the model converge, we'll have optimal generator, which generates samples that is very close to the reality. And in the end, discriminator, because generated samples are too close to real samples, the best strategy they can take is to just output 0.5 or random guess. So in our case, what we are doing was predicting or generating the trajectory, which contains origin destination information and the route choice. So we formulated the problem as follows. So we have state, which are the current and previously visited links. So in this network, we have some kind of trajectory that is kind of flowing into this network. And then we have action defined as this interlink transition, such as turn left, go straight, turn right, or terminate the trip. So it's doing link-to-link generation, but while kind of considering the distribution of future trajectory. So we feed in the real urban trajectory data. So we collected some taxi trajectory data from this Gangnam district in South Korea, and we trained the model to generate realistic trajectories. So in evaluation, we want the trajectory. So when we are generating trajectory, we want the trajectory to be realistic as individual trajectory, meaning that if we take one sample and then look at it, we want it to be realistic. But also, when we generate large, massive amount of trajectory data, then this data set should have some similar distributional pattern or distributional properties to the original training data or original trajectory data that we used for training. So we divided the performance evaluation into two, one in trajectory level and the other in data set level. So in trajectory level evaluation, we have the purple bar representing the proposed method that outperforms other models. And especially when it comes to the real world data that we collected from Gangnam district, it has more than 6 to 23% performance improvement. And especially it has less standard deviation, meaning that it's stable in terms of generating realistic trajectory. Also, when we look at data set level results, so if we increase the complexity of the data set, we expect that the model will perform worse. So meaning that it'll have points above. But you can kind of see that the purple line here, kind of representing the proposed model, is the best model in terms of robustness to the complexity of the data set. So to kind of quickly summarize this part, we have TrajGale model for reproducing realistic mobility behavior by generating trajectory data. There are several applications that we mentioned in the paper, such as we can resample trajectory data to resolve privacy issues because trajectory data has a lot of privacy sensitive information, but then we can train such generative model to resample it, kind of eliminating the privacy sensitive part, but only keeping the mobility behavior part. Also, this kind of generative models can be used to generate data or augment the data for training other neural networks for other downstream applications. Also, because this model specifically is a trip generation plus route choice model in the end, so we can replace the routing engine of traffic simulator to this kind of generative model to represent more realistic OD distribution and route choice behavior in the network. So afterwards, so that was my PhD study. Afterwards, I started my postdoc, and from there, I studied more on other topics too, such as traffic forecasting, network traffic forecasting. But one of the topics that sparked my mind a lot was this microscopic trajectory data. I started the study while I was a postdoc and kind of finished this study quite recently, like 7 months ago. So thanks to the advancements of computer vision and object tracking and all of those technologies, now we have a very scalable method of collecting microscopic trajectory data. So for example, we can fly a drone like this to observe an intersection and then collect trajectories of vehicles, pedestrians, bicyclists, So from these, we can also understand driving behavior, pedestrian behavior, or vehicle to pedestrian interactions. Oh. Okay, so in this study, we call it TrajFlow. So what we are trying to do is motion forecasting. So for ITS or autonomous vehicles to operate safely and efficiently, they should reliably predict future motion or future trajectory of surrounding agents. So for example, if you're using it for intersection monitoring, it should be able to predict trajectories of vehicles entering the intersection, pedestrians crossing the road, and everything. But when you think about this prediction setting, there has been a lot of methods that use deterministic forecasting. But then the nature of prediction, it inherently has some uncertainty in future motion. In future motion. So what we are taking is a probabilistic forecasting method to model the distribution of future motion. And also, there are several studies that represent the trajectory, represent the data as a trajectory, meaning that it kind of uses this kind of representation of the data, where we are looking at the trajectory of individual trajectory of pedestrians and vehicles. But also, nowadays, there are more studies that use this kind of occupancy density, where we are interested in predicting whether one agent will occupy that cell at certain time step. One of the benefits of the occupancy density is that, at least in our paper, it can produce infinite and continuous forecast over future motion, regardless of how the training setup was done. So for trajectory prediction model, they usually set up very short, fixed time step for their forecasting. But for occupancy density, we can predict infinitely. So in this paper, we use a model called, or a generative model called normalizing flows. So in a nutshell, the idea is that we are learning this flow layer, and then we are assuming that this flow layer is invertible. And as other generative models do, we are starting from very simple distributions, such as Gaussian distribution, and then learning to transform this distribution into complex distribution, such as the motion of agent. And because they have this assumption, because this model has this assumption that the flow layer should be invertible, we can actually use change of variable theorem to derive exact expression of the likelihood function, meaning that we can use the likelihood function to train our data, train our model. So compared to other models such as VAE or GAN, which doesn't really support that kind of feature, normalizing flows has the advantage in terms of doing exact log likelihood estimation or evaluation, meaning also we can also use that information to represent the distribution of prediction after we train the model. So the idea is that we have some previous locations such as coordinate of the location and the speed, acceleration, heading, class of the agent. We kind of use some condition encoder. In this case, we use two different types of encoder, one based on recurrent neural network and another one that's based on neural control differential equation. And then we are training, we are feeding that information into normalizing flows so that we can train or we can learn the conditional distribution of future motion given the observation and the features around the agent. So here's a quick overview of the result. So we have two tests, one for pedestrian trajectory and another one for vehicle trajectory. And across different data sets, we can beat the state-of-the-art performance. And also, we can use the model to generate predictions like this, where the contour map kind of represents the distribution of this agent at future time steps. And we are kind of exploring how to use this kind of model for downstream applications, such as monitoring intersection safety, as I mentioned, also kind of using it to understand the interaction behavior of interaction behavior between pedestrian to pedestrian and pedestrian to vehicles. Oh. What's wrong? What's wrong? Okay. So, quick summary of two studies that I presented so far. So the first one is trash gale generating macroscopic trajectory. The second one is the trash flow, which does the probabilistic prediction of microscopic trajectories. So one of the research questions that I started asking after finishing these two studies was that, so training this kind of generative AI, deep generative model, requires massive amount of high quality data collection, meaning that to do the first study, we need a good set of trajectory data to start with. And to do this kind of probabilistic prediction, we need a good set of microscopic trajectories. But this may not be realistic in many cases, especially in transportation. So the third study is training generative model without fully observed data and sampling full data using the pre-trained generative model. So we are applying the idea to traffic state estimation, and we are using a model framework called diffusion model. I'm going to kind of elaborate more on that. So traffic state estimation, as you kind of have heard before, it's reconstructing traffic state given very sparse observation. High resolution traffic state is essential for operation and research, but collecting such high resolution data is very hard. So that's why still many traffic monitoring systems rely on loop detectors and probe vehicles. And there are other methods or other systems such as I-24Motion, which collects high resolution trajectory data from multi-camera system. Or there's PNUMA dataset, which collects trajectory data from drone videos, but they are very expensive to deploy. So the idea behind traffic state estimation is to reconstruct this kind of high resolution traffic state from this kind of very sparse and noisy sample. So actually, we can think of traffic state estimation as inverse problem. So inverse problem is where we have some certain true data. I'm not sure why my slides are not updated. I'm sorry. So we have our true data, but then we have some kind of degradation operator that is applied to the true data, and then we have only access to this y. Okay, so the goal is to sample x, so sample true data given the measurement y. So to represent it in a probabilistic distribution is p x given y. So it's a posterior distribution of x given y, and it describes all feasible, all possible, all plausible traffic state x given some observation y. Okay, and if you are familiar with Bayesian formulation, we can kind of decompose this equation into two parts, where the first part represents the likelihood and the second part represents the prior. And the likelihood kind of measures how likely is the likelihood, how likely is the measurement if the true state were x. And prior encodes our knowledge about what's valid or what's plausible. So there can be different aspects around it, but we can kind of decompose it into data-driven prior, which means that we learn some distribution using data. And we have model-driven prior, which we constrain the model or constrain the sampling process to follow some pre-known knowledge, such as traffic flow theory. So we start from this equation, and then we can use this kind of logic to derive this equation, kind of decomposing the prior part into two. And the likelihood we can define by using some Gaussian distribution maximum likelihood estimator. Also, we can use some feasibility checker or projection layer to check if the generated traffic state follows some physical rule by using this kind of operator. So say we have this equation ready. So now the question is, can we actually train this p data x just from y, which is the noisy sparse data? And the second question is, can we generate meaningful X given Y? Meaning that can we sample X, keeping X to be constrained within this kind of physics regularization and minimizing this part right here. So that's the idea behind this study. So for solution one, to answer the question one, we are using diffusion model. So to kind of give you a broad or general idea, the model starts from very clean data and then start adding very small noise at a time until it reaches complete noise. And we are learning to denoise this process so that we can start from very complete noise to reconstruct the full data. So this notation here requires the full data observation, but we proved that we can do the same thing by only using our measurement by further corrupting this Y. So we select some of the parts that we observe, but then we use those parts to further mask out and then train diffusion model to reconstruct this part. And we can prove that this objective match with training the full data distribution. And secondly, we can actually answer the second research question of predicting or generating X given Y by having this physics-guided posterior sampling method. So the idea is that we do diffusion reverse step every time. So we do this diffusion reverse step. But then at this step, we do the projection to the plausible plane by doing observation projection and physics projections to keep the generated result to match with observation. Also to make it align with physics that we know in traffic flow theory. So in the experiment, we use I-24 motion data to start with. So we have this complete data. But for training, we are using this kind of data where we have very sparse, noisy observation. And then the goal is to reconstruct this state from this kind of data. So we need to check two things. So first of all, we need to check whether we can train this P data X. So we have three different methods. So we have full ops and two different proposed methods. So full ops means that we have full observation of the data. So we are essentially using this data to train our model. So this kind of gives the upper bound of the performance. So meaning that if we can reach this performance, then it's good. So as you can see, especially when we are using the sampling method that I'm going to present in the later slides, we can actually achieve very similar performance to the upper bound of the performance when we have smaller observation and more observation. Secondly, we want to check whether our physics-guided posterior sampling method can generate realistic traffic states. So we compare the model with purely model-driven method, purely data-driven method, and our method, which is a combination of. So from here, we can also see as we have more observation, we have smaller error, but still we outperform other model even though we don't have much of observation. So these are all numbers, so it doesn't really make sense mostly. So I prepare some qualitative result. So these are the observations that we use. So we train a diffusion model using this data. And then we use our pre-training and sampling method to generate data like this, while this one is the ground truth. So you can kind of see that it really matches with the ground truth. And even we can do it with very small measurement. So I think this one was around 10% observed over full time space diagram. So as you can see, it also can generate very realistic time space diagram given very small amount of measurement. So from here, I kind of presented that this model can learn traffic state from sparse noisy data. Also, it can sample plausible traffic states from sparse observation. And we believe that, and we are working on generalizing this method to other inverse problems in transportation domains, such as trajectory reconstruction, OD route choice estimation, and travel survey imputation. So to kind of conclude my presentation, so in this presentation, I showed that DGMs can be used to learn the distribution of transportation and mobility data. So we have GAN-based model generating macroscopic trajectory, normalizing flows-based model for probabilistic prediction of future motion, diffusion-based model for traffic state estimation. And there are more and more studies or more and more topics that you might want to see if DGMs can solve better than other models. And there are a few next steps that we are doing. So first of all, we are considering the scalability of the model. So can we actually, or how can we deal with a large amount of factors, large number of factors in data generation process in modeling this generative model? Or can we actually make, or how do we make, or how do we ensure the trained model works with out of distribution data, meaning that we want to generalize it better, especially for autonomous vehicles, vehicle-related studies, because crash data is very rare. But still, we want generative AI to understand what crash is. And we are also thinking of kind of coding the causality into the model so that we can do some what-if analysis using deep generative models. So if you're interested, so from this presentation, if you're interested in looking into more about generative models, so we have this paper published in Transportation Research Part C. So what we offer is, I'm not sure if no. So what we offer is that we offer introduction of all the methodological or mathematical derivations of deep generative model. And we have a survey of all the state-of-the-art generative models applied in transportation domain. And finally, we have a tutorial section where we present, and we have open source code. You can go to this GitHub repo, where we have code examples of variational autoencoder, generative adversarial network, normalizing flows, and diffusion model applied to traffic state estimation and household survey generation. So if you're interested in it, please go ahead and then read our paper and then try our code. And also the two last parts of my presentation, we are presenting this at TRB. So if you are attending TRB, please come to our poster and then have more discussion. Not sure if I did a good job on time. Thank you. This was it for my presentation. So if you have any questions, please ask. I can answer. Thank you.
Such a fascinating talk. I have some questions, but I will maybe see if there are questions from the audience who want to ask first.
Yeah, I would like to ask a question. Thank you for the very nice talk and the resources. Just a clarification, a curiosity. The clarification question is where the ground truth in the traffic state estimation, where it comes from? And the curiosity is in the first paper, you have trajectory generation, and in the second part, you have prop data. And I am wondering if you are thinking on bridging the two studies, because in one you have trajectory, in the other traffic state. So do you see the future on connecting the two worlds?
So first of all, the first question, so we get the ground truth data from I-24 Motion. So it's a data set. They have cameras on highway I-24, and they collect trajectory data. And from there, we can find a lane-based speed for each cell. So that's our ground truth data. And the second question is very interesting because that's one of the things I was kind of thinking, but I didn't have the word to put in. So kind of combining these two, we can actually build something like optimal trajectory or optimal route planning for observing the full state of the urban network. So that's very interesting idea, and that's something to think about too.
Thank you.
Yeah, I have a question about the first part of the talk. So, the first part of the talk, you know the beginning few steps of the trajectory, and you're predicting the rest of it, right? So, I wonder, did you compare the GAN approach versus the supervised learning approach? So, because this task, it seems like it can also be formulated as a supervised learning, instead of a generative.
So maybe I didn't do a good job of explaining this in a very short time. So we start from nothing, and then we build up the trajectory. So we don't, but then in intermediate state, we have some trajectories, links, that is also generated. So essentially, we start from nothing, and then we generate our origin location, and then we select the next link, next link, until the model decides that it has to terminate the trip.
I see. Okay.
And then I think the second part of the question is whether I compare this with some kind of supervised learning approach. So here we use RNN as one of our baseline. So RNN is trained as if it's a supervised learning. So it's predicting the next location at a time without considering what's going to come or the distribution of future trajectory. So, and there are many studies also like that. And especially like ChatGPT is doing the same thing, because ChatGPT is just predicting the next word at a time. But then it doesn't really consider what's going to come in the future text. So RNN model here is kind of like that. TrajGale model tries to embed the distribution of feature into the generation process.
So, so what is of the
Sorry. Sorry, guys. Sorry. That was embarrassing.
what's the input of the generative model in this setting? Like, do you need to consider the demographic information of the agent when you think of like because you have a comparison of individual trajectory, right?
Oh,
So I was
okay.
thinking, for example, if you have one road that is tolled and the other one is not tolled, then which one is going to be chosen is going to be dependent on the income level and all that.
Yeah, so that's also a very good question, and that's one of the topic that we are working on. So in this study, when we did it, we just considered every agent to be same. So we are just treating all as an equal and then generating trajectory. And especially this area is very commercial area. This is Gangnam from Gangnam Style. So, so it's very commercial area, very busy area. So we didn't expect that much of demographic distribution here. But then what you just said is more like, if you have different income level, different spatial distribution, demographic information, you can also use that to condition the model to generate different type of trajectories. So that's one of the things I want to work on and try to work on. One of the challenge is the data of collecting such large amount of trajectory data with different demographics. But kind of combining idea of this with the third one again, we can also infer because the third one, the idea is to use sparse data or missing data, data that has missing parts to construct a full data. We can also use the idea to train a general generative model that can do such thing without having to collect that high quality of the data, if that makes sense.
That makes sense. Yeah, thank you. Jill?
Thank you so much, Professor Choi. It's a really amazing presentation. I guess I have like an overall high-level question in terms of all those like generated data. So like as you mentioned at the very beginning, we generate those data. We want it to be similar enough with the original data, but also we want it to be different enough. Otherwise, what's the point, right? So I'm guessing like how do you evaluate that? How do you kind of do that trade-off? And especially for the first work, I think you mentioned some solid comparison in terms of the improvement that you did. Like, what's the metric you're using over there? And you also mentioned like improve some complexity or something. Can you like go further? Like you maybe use that as an example to explain that question.
Okay, so very good question. Thank you so much for that question. So if I can elaborate more on that, so you're asking about whether, so we want the generative model to represent a distribution. So we should measure how close that distribution that we learned is to the actual distribution. But as if we use ChatGPT to generate multiple different things, we wanted to generate diverse data or diverse data samples so that we get something more than that. Okay, so to kind of answer the first part of the question, so actually let me see if I can find a better slide to answer that question. So to kind of go into detail, we used two types of data sets. So one is based on traffic simulator. So we are simulating trip generation and route choices, and then we are using that as our proof of concept data. And then we are using Gangnam data, the taxi trajectory data, as our real world data. So you can kind of imagine from here. So in this case, we have single OD, meaning that we have only one origin destination. And we have some demand pattern like this, kind of going from left to right. And the third one is we have two-way demand pattern where we have one demand coming from left to right, and then one demand coming from right to left. So as you kind of go from this one to the real world, then you can kind of imagine the complexity of the distribution is kind of increasing. And we actually use we can measure the link-to-link transition, and then we can measure the entropy of the link-to-link transition probability to measure the complexity of the data. So that's how we measure the complexity of the data. And we compare the Jensen-Shannon distance, which is a metric to compare two distributions. So how close, so it's a distribution metric for a distribution. So it uses KL divergence, which is Kullback-Leibler divergence, and then measures the difference between distributions. So it measures how close our generated data set is to the training or the validation data set that we're using. So that's the answer for the first question. The second part is kind of related to the next steps, because to do such diverse generation, I think we need this part where we should be able to do what if analysis or simulate what if scenarios, because currently DGMs heavily rely on training data. So it doesn't really, so it knows how to generate samples that are not in reality, but we cannot guarantee that those are actual realistic data. But then if we can prove that by using some causal inference, causal structure behind the scene, then we can, and then use it to simulate what if scenarios and what if analysis, then we can actually call that generated data is valid and realistic. So I hope that answered your question on the second part. Yeah, thank you.
Okay, thanks so
Thank
much.
you so much, Professor Choi.
So we're at time, but if there is a quick question from audience, we can have that. Otherwise, we're gonna conclude. Okay, great. Thank you very much. And then thanks everyone for attending this seminar. Songjun, this is a wonderful talk, and thanks so much. And also, I know it's pretty late on your local time, so thanks for staying late for giving this talk. Thank you very much.
All right, thank you. Thank you so much for inviting.
Okay.